Hello. The purpose of this video is to provide support for the graphing of our data from the volume of water versus rocket height lab. So you can see here that I have previously set up the graph paper. I took a picture of a graph paper, and unfortunately the names of the axes have been cut off. You can see here on the x-axis we have our independent variable, the variable that we manipulated as the experimenters, the volume of water we placed in the film canister. And on the y-axis, we have the dependent variable. And this will be true of all the graphing we do in science this year. We have the dependent variable, the result of the changes in the independent variable, which is the height of the rocket. The next thing I did, going back down to the x-axis, is just try to spread out the data. I looked at one class's data, and it looked like the biggest volume anybody used was 24 milliliters. So I just went every 4 lines. Notice we're graphing on the lines, okay, because we're going to be using the coordinate planes here. And if I needed a 30 milliliter mark, I could just go out and count 4 more lines, and now I'm at 30 milliliters if needed. And then I looked at the height data, and I think there's probably a 4 meter or 400 centimeter height of launch in the table, but I basically ran out of room. But I think we'll get the point across here. We'll get a good scatter plot of data regardless of not having those highest points out there. So now we're graphing in the coordinate plane. So I'm looking, you can't see it, but I'm looking at the data for one of the classes, and I noticed, for instance, there's a data point for a group that used 5 milliliters of water, which is about right here, and that rocket launch for them went 220 centimeters. Notice that we're converting all the meters to centimeters. It's good practice. So as you know, we're graphing in the coordinate plane. So this is actually a point in space on the x and y grid, if you will. So I'm traveling up to the 220 mark, which is probably about here. If that goes from 200 to 250, then halfway is 225. So 220 is probably roughly in here. Now, keep in mind we're not being exactly exact. We're just trying to scatter. We're just trying to plot our data so we can get a sense of the trend. Next up, I see that a group has a piece of data at the 10 that did a launch at 10 milliliters, and that launch went 150 centimeters, 1.5 meters up, and that's that position right there. And again, I just make a simple dot to represent that piece of data. I don't have to put the coordinates there. We can figure out the coordinates if we needed to. We could just work backwards and notice that this is at 10, 150. Notice that the x coordinate always goes first, x and then the y coordinate. And now I'm off and running. It gets a little bit faster as you kind of get used to it. I see some group had a launch at 8, and it only went about 50 centimeters, half a meter. A group had a launch at 20 milliliters, and that one did pretty well. Went up to 3 meters. I think over one. And off we go. Now, I'm just going to kind of jump ahead and throw some data in here, because the last thing we want to do now, since once we have one whole class worth of data in our graph, so we're making a scatter plot. Okay, no judgment, no bias. We're just plotting the data that we have. It is what it is. And then the next step would be to look for a trend. Now, I had suggested in previous classes that we would make a trend line with this data. But after further research, it turns out that this data does not lend itself very well to a trend line. It's really more of what we would call an optimization graph, or an optimization problem. Because if you look at it here, and you can imagine from your own data, from your own observations, that there's a bit of a parabola here. There's kind of a curve in our data. So what happens probably is that as we add water to the film canister, we get a really good reaction, lots of substrate, water if you will, plus the tablet, leads to a high amount of carbon dioxide being released by the effervescing of the tablet. There's a large volume of gas in the film canister, and therefore a large amount of pressure, and thus more force for that launch. However, at some point, somewhere around 16 to 20 milliliters, it looks like the data begins to drop off, and the rocket launches decrease. And my thinking is that perhaps at that point, even though there's lots of water and therefore lots of substrate for the reaction to take place, lots of carbon dioxide could be produced, there's no longer enough, literally enough room inside the film canister for much gas to be produced, and therefore less pressure is being produced. So you don't have to draw a trend line unless you want to, and hopefully this explanation also will help you to answer a number of the analysis and conclusion questions in the lab packet.